Hi, my name is Jialun Liu, and in this video, I'm going to talk about our magnetic sensor-based localization method for autonomic dislocation of ingested button batteries. Button batteries are found in many household items such as toys, TV remote controls, and so on. Children explore their environment through all their senses, but when they taste, they are at the risk of swallowing dangerous objects such as button battery, which may lead to severe internal tissue damage. Button battery ingestion is a frequently reported incident, happening to over 3,500 people every year in the US alone. When analyzing the medical record of 76 children, one study found that in 87% of these cases, the children were aged between 0 and 6 years. The ingested button battery can cause severe damage to the stomach surface. It could lead to surgery, mouths with feeding and breathing tubes, and even death. In our previous study, an experiment was conducted to assess the possible damage of the stomach wall caused by the battery. The figure displays the degradation of the tissue that happened in only 30 minutes, and other studies have shown that the lining of the stomach can be burnt in just 2 hours, and ulcerations can occur in 5 hours. The National Capital Poison Center provides a typical guideline for treatment of an ingested button battery for toddlers and children. X-ray is needed immediately, because the battery lodged in the stomach may cause severe burns in 5 hours. Then, if the button battery is inside the stomach, it should be removed endoscopically if possible, or surgically if the endoscope is not available. The detection and the localization of an ingested battery is still a challenge, needing an accessible technique that does not depend on costly medical imaging methods, such as ultrasound, fluoroscopic imaging devices, or MRI. And some of the imaging devices are invasive by radiation. The treatment of an ingested button battery is always very urgent. However, not all the hospital and local doctors have these costly medical imaging devices. Also, experts are needed to operate the devices, and doctors need to be proficient in using endoscopes. It is always be very hard to fulfill in all these conditions. Therefore, we need to develop a non-invasive and low-cost method with less expert knowledge required. In order to explore such a method, we previously developed several ingestible robots. In 2016, we presented an ingestible origami robot for patching stomach wounds. The origami robot was packaged in an ice capsule, and after the patient takes it, the capsule lands on the stomach surface and melts. Then the robot can perform treatment for stomach. There are mainly 5 challenges when we explore the new treating method. In this paper, we will present the detection of the button battery and the navigation of a robot, and the dislocation of the button battery. The robot transportation and healing were studied in our previous work. The isolation and transportation are mainly about trying to avoiding the robots contacting with the stomach wall and letting it to be excreted out the human body. Here, we proposed a novel method for the localization of the button battery based on the fact that the button battery can be remotely magnetized with a direct magnetic field to a magnetic strength level that can be sensed by magnetic sensors. There are 3 stages in our demonstration. Localization. We first perform the localization of the button battery. A horizontal electromagnetic coil, which is able to produce a vertical magnetic field, is installed under the button battery. Once the vertical field is applied, the button battery is magnetized. A sensing board with magnetic sensors is installed 10 mm under the button battery. We use these sensors to get the position of the button battery via trilateration. The second stage is navigation. Our platform also has 2 deep quantum stomach that creates a stimulated environment of a child's stomach. An interventional magnetic capsule is placed inside the stomach, and 4 surrounding coils of our platform are activated to navigate the capsule to the position of the button battery. And dislocation. Once the battery and the capsule are attached together, we activate 4 coils to dislocate the button battery together with the capsule. We model the magnetization of the button battery under a magnetic field. The autonomy of the LR44 bottom battery is shown in this figure, and where the soft magnetic parts are colored red. These two parts are made of ferromagnetic materials with high susceptibility. Thus, the battery can be modeled as a hollow ferromagnetic cylindrical object. We found that the principal magnetization of the bottom battery occurs along the longitudinal dimension of its body, based on the finite element method. We assume that when an external magnetic field B coil is applied to the bottom battery in the positive direction of the axis, magnetization M is produced, and it takes the shortest path connecting to two farthest locations inside the body, which are point A and point B in two figures, makes them south and north poles respectively. Due to the symmetry of the body and the magnetic field, A and B are not fixed at certain locations on the edge of the bottom battery. However, the distance between two poles remain unchanged. Therefore, the Z component of the principal magnetic moment mz only relates to the intensity of the applied field. Here, the magnetic flux density of the applied field is around 8 millitesla, providing a sensible range of 31 mm for the bottom battery. The basic method of trilateration is taken in our localization method. This figure shows the locations of the magnetic sensors and the bottom battery on the working surface. The vertical distance between the sensor and the battery is 10 mm. This distance setting depends on the sensitivity of the sensor, which can be regulated in the future. The sensors are arranged on multiple hexagonal PCBs spanning the space, such as the covered area can be flexibly expanded. In each hexagonal board, 3 magnetic sensors are implemented as equilateral triangle. Then, we could use the method of trilateration in each triangle. Let D become the side length of the equilateral triangle, and XYZ become the position of the battery. Then, we can get the coordinates of those points in the figure. RA, RB, RC indicate the radii of the 3 spheres for trilateration method. Then, by solving these 3 equations, the intersection of these 3 spheres, XYZ, is derived. There are 21 sensors in our sensing board, providing 25 available triangles. The total sensing area is around 25 cm square. The figure shows the comparison of the estimated localization results and the real locations of the bottom battery, which are marked as blue circles and red crosses respectively. The black dotted circles are the sizes of bottom batteries. It can be seen that it is possible to detect the bottom battery within an area of less than the size of it. Expect the horizontal poles of the battery. The overturned sitting poles was also considered, where the battery places its cylindrical face on the ground. This figure shows the localization result of both postures. The proposed system can also autonomously dislocate the accidentally ingested bottom battery inside the stomach. The video gives the entire demonstration. We place the bottom battery at a random position, then magnetize it by applying vertical magnetic fields. The system averaged and filtered the sensing data, then ran the detection algorithm. Among 20 trials, the average time taken for bottom battery detection is 2.2 seconds. After that, an interventional magnetic capsule was placed inside the stomach. The system searches for the locations of the capsule, derives the orientation and distance, and generates the robot trajectory so that the system can control the coils to apply appropriate magnetic fields to autonomously navigate the capsule to the bottom battery. After the capsule attaches itself to the battery, the system detected the attraction and dislocated the battery. In our paper, we proposed the low-cost localization method for detecting an accidentally ingested bottom battery using electromagnetic coils and an array of magnetic sensors. The method is applicable for a certain range of ferromagnetic materials with high susceptibility. We also demonstrate the button battery localization and dislocation. Thank you for listening.